the last lecture, we have seen some of the important properties of the first row transition metal ion, that is the formation of alloys and other compounds and the variable oxidation state of the transition metal ion. In this lecture, I am going to give you the two important properties of the transition metal ion, namely magnetic properties and catalysis by the first row transition metal ion. Let us first start with the magnetic properties. When you place any compound in a magnetic field, then there are two type of a behavior is being observed by the compound. Either it will be attracted by the applied magnetic field or it will be repelled by the applied magnetic field. In this case, you will have two type of a behavior, namely diamagnetism and paramagnetism. Diamagnetic substance is generally repelled by the applied magnetic field, while the paramagnetic substance is being attracted. The substance which are attracted very strongly by the magnetic field, in fact, it behaves as if as a magnet, is known as ferromagnetic substance. The transition metal ion can behave in all three ways, that is, we can expect diamagnetism, paramagnetism and also the ferromagnetism in case of a transition metal ion. Some of the compound and in native state, iron, cobalt and nickel can exist as a ferromagnetic compound also. This ferromagnetism is in fact is an extreme form of a paramagnetism. As I said, most of the transition element and their compound show paramagnetism, and paramagnetism arises due to presence of unpaired electron. Each electron has contribution towards magnetic moment. The magnetic moment of any transition element or its compound or ion is given by formula mu s is equal to under root n plus 2 Bm, where Bm is the unit to measure the magnetic moment and it is called as Bohr magneton, and n in this formula represents the number of unpaired electron in the metal ion or its compound or its ion. One thing to be noted here is that the mu s given by this formula is called spin only magnetic moment. Sometimes the symbol mu SO is also used in place of mu s. The total magnetic moment is a sum total of two type of a magnetic moment, namely spin only magnetic moment, and in addition to spin only magnetic moment, there will be a contribution to the magnetic moment by the orbital motion of an electron. As you understand, the electron has two type of a motion, one is spin motion and other is the orbital motion, similar to the rotation of an earth around the sun. Therefore, if we ignore the orbital contribution to the magnetic moment, then the spin only magnetic moment will be calculated by this formula. This is what I was talking initially, that in the absence of magnetic field, all the electron will randomly align, but the moment the magnetic field is applied, all the electron will ally in a one direction and will results into the paramagnetism. If they anti-align to the magnetic field, then there will be diamagnetism. This table shows the spin only magnetic moment values of the various ion of first transition metal ion. Starting with the scandium in +3 oxidation state, as you are aware, in its electronic configuration, it is 3d0 and therefore, there is no unpaired electron, and therefore, the magnetic moment will be 0, or in other words, the scandium 3 plus and zinc 2 plus will be diamagnetic, having 0 magnetic moment. Starting with the titanium having one unpaired electron in the d orbital, going to give you 1.73 unit magnetic moment. In fact, the observed magnetic moment is very close to the spin only magnetic moment, which is 1.75. In this series, the paramagnetism first increases as we move from titanium to vanadium to chromium to manganese, and it is highest in case of a manganese. The magnetic moment is somewhat around 5.96, but in the middle of the series, as I said, it is maximum, and afterwards the number of unpaired electron decreases, and therefore the magnetic moment also going to be decreases and reaches to 0 in case of a zinc metal ion. How to measure the magnetic moment? There are two methods to measure the magnetic moment. One method is Gauss balance and other is the Faraday balance. The Gauss balance is simplest among all, in which simply compound is placed in the magnetic field and the change in the weight in the compound is generally measured. If the compound is being attracted by the magnetic field, then its weight will going to increase. This results into the paramagnetism. However, if the compound is diamagnetic, then there will be no change will be observed, or either there will be decrease in the weight will be observed in case of a diamagnetic compound. In fact, other than the iron and simple compound, transition metal ion do form a varieties of a complexes. We shall be going to learn about these complexes in another episode, but here I would like to say you one thing, that if the complex is also placed in a magnetic field, then there will be two type of an orientation is possible. As you are aware, the d orbital under the influence of the external perturbation is going to split into two sets, namely Eg and T2g, out of which the Eg, that is dx square minus y square and dz square, will be having higher energy, while dxy, yz and zx will be lower energy. And therefore, if you have first 3 electron, then they will be of course occupying the lower energy dx square minus y square, lower energy dxy, dyz and dzx orbital, and the fourth electron onwards will have a two choice. Either it will get paired into the same orbital, or it will remain unpaired by entering it into the higher energy dx square minus y square and dz square orbital. Depending upon this, two cases will be there, that is either you will have a paramagnetism or you will have a diamagnetism. Let us understand this by the example of iron complexes. If iron, here there are two complexes of an iron is given, one is a cyano complexes, another is an aquo complexes. In the one complex, cyanide is very strong ligand, because both the complexes are octahedral, and therefore, the delta value is very large in case of a cyanide, because of it is strong ligand, and delta value will be smaller in case of a aquo complexes, because water is a very weak ligand. Therefore, depending upon the delta, the electron will try to get paired into cyano complexes, resulting into all the 6 electrons are paired, and therefore, it will be low spin complex or diamagnetic complex. However, in case of an aquo complex, after the fourth electron, fifth and sixth third electron, fourth and fifth electron will enter into the higher energy Eg orbital, and the only sixth electron will get paired into the lower energy orbital, and therefore, resultant there will be 4 electron remain unpaired, and therefore, this is called as high spin complex or spin free complex, and it will be paramagnetic. So, as I said, first 3 D1, D2 and D3 complexes will be always low spin complexes, but D4 onwards complexes can be either high spin or low spin, depending upon the value of delta and pairing energy. If the value of delta is very large, then electron will try to remain paired, but if delta is small, electron will try to remain unpaired, and therefore, depending upon this, we can observe diamagnetism and paramagnetism. The next very important property of the transition metal ion is the use of the transition metal ion, its compound and its complexes in the catalysis. As you are aware, the catalyst is very important as far as the 90% of any processes is incomplete without the catalyst, and the transition metal ion is very important as far as the catalyst is concerned. These metal ion and their compound are acting as a catalyst because they are important catalyst in industry as well as in the biological compound also. This table gives some of the important metal ion and their compound in the catalysis. To start with, we have a titanium in form of a TiCl3. It is used as a catalyst in the famous Ziegler-Natta catalyst which is used for the production of polyethene. From the ethene, polymerization of ethene leads to polyethene by Ziegler-Natta catalyst, and here titanium in form of a TiCl3 is used as a catalyst. Another example of an catalysis provided by V2O5, that is vanadium compound, which is used in contact process to oxidize sulfur dioxide to sulfur trioxide. Iron is also used as a famous catalyst in a good old days, as well as in today's industry. We are using iron as a catalyst in a Haber process, conversion of nitrogen and hydrogen to give you ammonia. Nickel is also very important catalyst in a hardening of vegetable oil, which is given by this reaction. Copper is also one of the important catalyst which is used for the oxidation of cyclohexanol or cyclohexanone into mixture of adipic acid, which is used for the production of nylon 6,6. So, therefore, vanadium, iron, nickel, cobalt, titanium, etc. are very important metal ion, and their compound are used as a catalyst in various catalytical processes. This catalytical property of the metal ion is due to three reasons. Number 1, presence of unpaired electron in their incomplete d orbital. Number 2, we have already seen variable oxidation state of a transition metal ion, and number 3, in most of the cases provide large surface area with the free valencies. Because of these three reasons, various transition metal ion and their compound are find uses in the field of catalysis. Here one example of a catalysis is iron 3 catalysis, which is reaction between iodine and persulfate ion. Now, the d block metal and their compound are using in a catalysis in two type of a main reaction, namely heterogeneous catalysis and in homogeneous catalysis. Apart from these two, there is a third process called Metalloenzyme catalysis, which we are also going to touch upon at the end of the lecture. Let us first understand why we need a catalyst. Generally speaking, the function of a catalyst is to provide an alternative reaction pathway of lower activation energy, and it enables the reaction to proceed faster than the uncatalyzed reaction. So, in other words, the catalytic reaction are faster than the uncatalyzed reaction. The catalyst and reactant can be either in the same phase or in the different phase. If they are in the same phase, then it is homogeneous catalysis, but if they are in different phases, then it is called heterogeneous catalysis. The most common heterogeneous catalysis is generally provided by the example in which the reactant are gases and catalyst is a solid. A heterogeneous catalyst provide a suitable reaction surface for the reactant to come closer and to react. The example, as I said, is a famous good old days Haber process. In this process, the synthesis of ammonia from 1 molecule of nitrogen and 3 molecule of hydrogen to give away 2 molecule of ammonia. This reaction is being catalyzed by the iron. Now, in the absence of catalyst, the formation of the gaseous ammonia proceeds at extremely low rate. Sometimes the conversion requires hours or days. This is due to collision of 4 gaseous molecules, that is 1 nitrogen and 3 hydrogen molecule is extremely small in the absence of catalyst. Moreover, this 4 reactant molecule will collide in a proper orientation in order to form the product, and the bond enthalpy of the reactant is very large in absence of the catalyst, because the reaction has very high activation energy, and therefore, you require to use a catalyst. In the presence of an iron catalyst, the reaction proceeds much faster, provides an alternative reaction pathway of lower activation energy, because here iron is a solid and the reactant, that is hydrogen and nitrogen, as well as product ammonia, is a gaseous molecule. The catalytic action occurs at the interface between these two states. The metal provides an active reaction surface for the reaction to occur. Gaseous nitrogen and hydrogen molecule will diffuse to the surface of the catalyst, and then the gaseous reactant molecule which are adsorbed, that is adhered on the surface of the catalyst. The iron metal having many 3d electron and low lying vacant 3d orbital forms a bond with the reactant molecule and adsorb them onto its surface and weakens the bond present in the reactant molecule. That is to say, the bond between the reactant molecule hydrogen and nitrogen will get weakened after absorbing on the surface of the iron, while the free nitrogen and hydrogen atoms, when come into the contact with each other, they will readily react and form the product. The weak interaction between the product and the iron surfaces, this is because the gaseous ammonia molecule adsorbs very easily. So, this is how pictorially we can understand the whole process in detail. First, the diffusion of the gaseous nitrogen and hydrogen molecules on the surface of the catalyst will occur. Then in the next phase, there will be adsorption of the reactant molecule onto the surface of the catalyst. As I said, here there is a weak interaction between the gaseous reactant molecule and that of iron surfaces, and because of this adsorption, the bond between them get weakened and the bond between the product, new bond between the product molecule will be formed. So, in the next phase, the breaking of the covalent bond within the molecule will occur, and a combination of the highly reactive hydrogen and nitrogen will form an ammonia molecule over the interface of the catalyst. And finally, after the formation of the ammonia molecule, this product has to be desorbed from the surface of the catalyst. The Haber process is very well known process for the production of ammonia, and it is discovered before 100 years, but the exact mechanism of this reaction was not known until the 2007. This reaction, this diagram will provide you the complete understanding of how reaction is proceeds with and without the catalyst. As I said, without the catalyst, uncatalyzed pathway is having very high activation energy, but under the influence of the catalyst, that is iron catalyst, the activation energy decrease very sufficiently, and therefore, the reaction proceeds in very faster manner, very rapid manner in the presence of the catalyst. As I was talking, this reaction, that is Haber process, is a backbone in the fertilizer industry, because the ammonia is a gas of great importance in the field of fertilizer production, and the mechanism of the complete formation of ammonia over the surface of iron was not known until 2007, in which the Professor G. Ertel from Germany has given a complete mechanism of the reaction between iron and the gaseous hydrogen and nitrogen molecule to produce ammonia. This leads to the Nobel Prize to him in 2007, and eventually he gave a Nobel Prize lecture, Reaction at the Surfaces from Atoms to Complexity. The another example of an heterogeneous catalysis is provided by the reaction in which the decomposition of an hydrogen peroxide occurs. Here the reactant is a liquid and the catalyst is MnO2 powder, which is a solid, and therefore, in aqueous or liquid state also we can have a heterogeneous catalysis. So, in earlier example the catalyst was a solid and the reactant was a gas, while in this case the catalyst is a solid and the reactant are in aqueous or in liquid state. The another class of a catalyst is homogeneous catalyst. In this also the transition metal ion and their compounds finds uses. Here, as I said, the word homogeneous means the catalyst and the reactant are in the same state. The catalyst form an intermediate with the reactant in the reaction and changes the reaction mechanism to another one with a lower activation energy. In homogeneous catalysis, the ability of the d block metal to exhibit variable oxidation state enables the formation of the reaction intermediate. One example of this type of a catalysis is being provided by the reaction between peroxo disulfate ion and iodide ion. The peroxo disulfate ion oxidize the iodide ion to iodine in the aqueous solution and themselves being reduced to the sulfate ion. So, this is how the reaction between iodide and peroxo disulfate to produce sulfate and iodine. The reaction is very slow and this is due to the strong repulsion between like charges. Here, if we use iron 3 as a catalyst, then the iron 3 will take part in the reaction and it will oxidize the iodide ion to iodine, and in this reaction the iron themselves get reduced to iron 2. In the next phase, iron 2 ion subsequently get oxidized by oxo disulfate ion, and at the end of the reaction iron 3 is regenerated. So, this is how iron 3 takes part into the reaction and it is regenerated at the end of the reaction. Let us see how the overall reaction takes place in the presence of the catalyst. So, this is a well known example of a homogeneous catalysis. The third example of an catalyst is being provided by metalloenzymes. You are all aware about the enzymes. Enzymes are the biocatalyst and they do carry out the reactions under very mild biological condition. Some of the enzymes or biocatalysts require metal ion as a cofactor and therefore, they are called as metalloenzymes. The example of the metalloenzymes are including the nitrogenous, which is a famous metalloenzyme in which the iron is used as a catalyst and it do the function of fixation of dinitrogen. The second example of metalloenzyme is being provided by the ceruloplasmin protein. It is a copper protein and it is utilized in the used in the utilization of an iron, and the main constituent of this protein, as I said, is a copper metal ion. So, like this there are many metalloenzymes contain transition metal ion, and therefore, transition metal ion is very useful in metalloenzyme also. So, in this lecture we have seen the importance of transition metal ion, particularly in magnetic properties and in the field of catalysis. In the next coming lecture, we will come to know some more important properties of the transition metal ion, such as the important complex formation reaction by the transition metal ion and the mechanism behind the colorful compound formation or colorful complexes formation by this transition metal ion.